Dr. Nijas Kunju. He's an application engineering manager at Ansys. He's specialized in the domain of RF antenna, radar, signal integrity, power integrity, and multiphysics simulations. Nizat has been working with Ansys from last 5 years, and he's providing technical assistance for all RF antennas, radar, especially in for driverless car and 5G MIMO applications. He has been interacting with engineers from different industries, which includes automotive, defense, RF and power electronics, and so on. And before he joined Ansys, he was working as a research consultant in GE Global Research in Bangalore on the area of microwave material sensing for detecting different materials in the crude oils. He has done his master's in electronic science and PhD under Professor P. Mohanan from Cochin University of Science and Technology, Cochin. And he's holding 20 plus international publication and 20 plus national and international conference publications. So I welcome you, Nijas, and handing it over to you to take it from here.
Whether you are able to hear me
Yeah,
properly.
now I can hear you. Yes.
Okay, so the screens are also visible, right?
Yes.
Okay, so today we are going to discuss about how high performance computing technology implemented in electromagnetics. And from the answers, we use a high frequency structure simulator, which is HFSS software for uh, almost 90% of application. Why I mentioned 90%? Couple of EM simulation can be done with some approximation in the electromagnetic equations like Maxwell equation. You can approximate some of the things and then solve it. So HFS is a full 3D, full Maxwell without any approximation we are solving there. But we do have a solvers for 2.5D solvers and quasi-static electromagnetic solvers for some of the low frequency and PCB kind of application. But today we will discuss predominantly on high frequency structure simulation and how the uh, high performance computing is implemented to get speed, memory reductions, and so on. Okay. So coming into electromagnetics problems, right? What all comes into that? So if you take one vehicle, it can be aircraft, automotive, or any of your day-to-day life electronics product. Okay. Uh, Give me a minute. Okay. So what you can say is you take one example and see from where you can take the application. Coming here, first thing it starts from the IC. So you take microprocessors, you take RFICs and MMICs. Take a simple example of an amplifier, which comes as a single IC for you. So this talks about the electromagnetic problem can start from the IC point. Then the IC where it will going to sit. It will have a PCB. So you need to solve how the signal is transmitting from the the IC, which is the die of the IC, which is silicon material. From that, how the signal is going to propagate through your black color IC package, then goes through the PCB, how the signal is going. So you starting from the die, then this is the wire bonds and other thing is called a package, which you may be seeing as a black color casing along with the IC. Then this will sits on PCB. So you need to simulate PCB. And then you probably see how the signal is transmitting from IC to another IC. For a simple example, you need to communicate from your processor to your memory chip, how the signal is going. And these all processor signals, right? It's our ones and zeros, but switching at very high speed. So they need to make sure, even though this switching at high speed, the signal going to transmit and receive properly on the receiver without much attenuation. Okay, that's one application. Now, another application for antenna applications, right? So if you see most of your electronics device nowadays in your hand has multiple connectivity with you. So you have a Bluetooth, you have a GPS, you have a GSM, 5G, 4G connectivities, and Now everything connecting and can be controlled through Alexa kind of application. So you need an antenna for communication. Some people, especially for defense, they need a high gain antenna. They use antenna arrays, multiples of antennas to get very high gain. So they can use it for long distance communication. So that's another application. Normally what happening is you will design this kind of antenna in a free space environment, but when you integrate this antenna on top of a mobile or laptop or any electronics gadget right nearby, because of nearby metals and other thing, shape's going to change. Another applications of electromagnetics are one you can say is RF interference. That's called co-site in analysis. What is mean is you take a your simple mobile where Wi-Fi, Bluetooth, both are working on the same frequency. And very next to that, there is a GPS. Then there next to that one, GSM bands are there, 5G bands are there. And these are all integrated in within like a centimeter in space. And all are working very nearby frequency band. What can happen when one is radiating, another it can affect the performance of the other. So we need to analyze and see whether if you have a multiple RF system on a device, whether it's going to work properly or not, right? RF interference analysis. Another one is, this is very interesting, the lightning. You might have seen so many videos where lightning is striking on a aircraft and it is still flying without any problem. And expected as per the calculation, every 4,000 flying hours, an aircraft can hit one times the lightning strike. And that is very common, but they need to make sure even though the lightning is happening, it should withstand the problem, right? If lightning happening, your entire engine going to shut down, then all the passenger may die. So they what they do is they do the lightning simulation. They try to identify how the current going to enter the aircraft, how the current going to leave from the aircraft. Since the aircrafts are made out of metal, the current will not penetrate in. But because of the skin depth and other thing, there will be small amount of current will get into the cabin of the aircraft. But they also want to make sure if that happened, their electronic system should withstand it. So they wanted to understand how the current is going to flow, how the electromagnetic wave is going to enter. Still, they want to make sure how it is going to withstand it. Next one is radar cross section. People might have seen big radars for defense purpose. They need to identify the targets in the kilometers of distance away, and they need to predict it. So how they need to do is they need to uh, find the target. They will send some signal and wait for the return reflected signal back to the radar. If I am developing an aircraft, I want to make sure if any signal coming, I should reflect the signal in some other direction, not in the same direction of the signal which is received at my side. So I will shape my aircraft. If it is a defense aircraft and other thing, I will shape my structure. I will use some kind of a absorbing coating which will absorb the signal, will not reflect the signal back to the same direction, so that the radar will feel there is no object, but actually there will be a target will be there. So that kind of radar cross section analysis we do. Large platform integration, we can say, when how the communication going to impact between your ship and helicopter when it is flying, something like that. Then electromagnetic pulse problem, EMP, which will say it is very common in a war scenario. In order to distract the entire communication, what the enemy will do is they will send a missile. It will not create a blast, but it will create a blast of electromagnetic pulse with a high power. So any electronic devices which is comes within a range of that blast will get, what will happen? It's burnout. The components, the IC components, everything will get burned, something like that. So there are a lot of applications where electromagnetics are using, and where the electromagnetic simulation softwares or computation method can help you to visualize or virtually model these scenarios and try to find a solutions. Okay, so these are some of the application where you can use the computation methods. Coming into that one, so if somebody is asking, I wanted to do a antenna simulations or the communication simulation, the basic block will be the antenna, and this is a simple model. Uh, as you as you do for any computational, what you will do, you will have is you will create a structure. You will excite, these all are different antenna. You will excite each antennas with some excitation signal, and you will set what frequency I wanted to simulate and a couple of material property assignments. That's what in a user point of view I need to do it. But we also need to understand how the electromagnetics are solving behind the computational softwares. Without that, all the electromagnetic solver, from my experience, it's a black box. If you are giving good information, good input, it will give you good output. If you give a garbage, it will give you garbage out. So try to understand any simulation software you are using. Try to understand how it is actually working, at least the basics of that. So I'll try to explain in the electromagnetic side. So this is what probably people will do. The electromagnetic side, what simulation software does in the background is they just divide the entire structure into small meshes. And electromagnetics equation, the fundamental four electromagnetic Maxwell equations are solving on the mesh, not on the CAD. Remember that one, because uh, if you are properly modeling the structure, but see your structure after meshing, if it is looking like this, do you expect a right result from numerical simulation software? No. If you are creating any model, you need to make sure your geometry going to represent properly in a using a mesh. Okay, so selection of a mesh, very important. And after this mesh, what happened is you will solve the electromagnetic equations. There are different method. One is integral equation method. Another one is differential equation methods. Then try to identify some of the unknown. So the unknowns can be electric field, magnetic field, surface currents, and so on. One of the quantity, if you can identify using the Maxwell equation, then rest of the all the other quantity you can recalculate using Maxwell equation. So you have some excitation voltage or power, that is your input. You have the material properties, boundary condition, then they will try to identify what is a field or magnetic field, electric field or surface current. Now, from these electric field and magnetic fields information, I can calculate which frequency this antenna going to work, what is the coupling from one antenna to another antenna, how the radiation patterns are coming up. These are all information I can calculate based on that. Coming back, one question, one step back, how you will identify whether the mesh is sufficient. So what is a calculation you will do if you want to solve some electromagnetic equations in a software? Do you need to take the mesh size as a lambda by 5 or lambda by 10? Lambda is nothing but wavelength, right? So that's the one question. Is that mesh is sufficient, or did I over mesh my structure? You can over mesh the model, no problem. But the problem is you are going to take up or end up with more number of simulation time, memory requirement, and so on. So there should be a compromise between, or there should be an easy way to find the right mesh for your structure, right? So for that, Ansys introduce a technology called adaptive meshing. So what it does in the background is very simple idea. You create your geometry and ask solver to run it. So what solver will do is it will create a just initial mesh and then try to see what is the S parameter or how the field is going to change. And then by default, it will improve the mesh. So you can see initial mesh is very coarse. It tries to improve the mesh quality by adding more and more mesh. So every time when it adds mesh, it will calculate how the response of my antenna going to change. If the response is not varying too much, what will happen? It will consider this mesh is sufficient for better accuracy. If mesh is the S parameter going to change a lot between my current mesh and previous mesh, it will keep updating till this S parameter going to converge. That's a good idea. And one more thing you need to see over here is the mesh become denser and denser wherever the electric fields are very strong. But the electric fields are not influencing too much on your structure. You don't need to mesh that area to very finer. So it does that calculation automatically for you. Okay, this is what I'm giving an example for how the electromagnetic solvers are working and getting an accuracy, what is mean by convergence and so on. Now, the second question is, I told you this simulation starting from the chip level, the PCB, and then you might have doing the antenna placement. The last simulation I simulated with a big city, right? So there are different requirement evolved or lot of challenges right now in front of us. Sometimes you need to simulate a very small piece of geometry. Sometimes you need to simulate a big city. The electrical size of your problem is changing a lot with the different requirement. So one solver for entire thing is not sufficient. So for that, what it does is there are different numerical methods are evolved, and most of the commercial software like HFSS adopted those uh, numerical techniques and they integrated together. So one option is, let's say this is highly complex. You can see when the complexity is going to high, you can see a simple chip is coming here, right? I'll show you why this is become so complex when in the electromagnetic problem later. So then the chip, then it comes to PCB, then it comes to waveguide, antenna arrays, and so on. So if you see these are can be solved using finite element method. If you go bigger and bigger problem with the finite element method, it requires a lot of memory and simulation time. Another electromagnetic method is the computation method is people will say method of moment, otherwise integral equation solver. It's solved predominantly on the mesh on the surface of the geometry. And since there is no, it's unknown is surface current, there is no radiation boundaries are required. So you will have mesh only on the surface of the geometry. Because of that, you can solve the metallic problems very easily, especially large reflector antennas. Reflector antennas are very common nowadays. You have a DTH in your home, right? That DTH antenna you can assume as a reflector antenna, that kind of antennas. Then antenna placement on a large metallic structures like aircraft and other thing, you can easily solve using method of moment. If the problem size is even bigger, something like a city and other thing, then what you will do is instead of solving the mesh, you will approximate the electromagnetic waves are propagating in terms of optical rays. So depends on the material property. If it is a dielectric or metal, the field will reflect it back or it can penetrate through. So that kind of approximation you can take when the electromagnetics simulation complexity or not complexity, the electric size is too big for you. Okay. When it comes to a practical problems, right, you will have a mix of this thing. What you can see is there is a big aircraft with very small antennas over here. So what you can do is you can use hybridization method. What it means is in a single geometry, different part will solve with a different solver. So you can ask this antenna to solve with a FEM solver and remaining geometry either with a MOM and SPR technique. That's called hybridization of solver. That significantly reduce memory consumptions and other thing. Okay, so there are solver techniques I'm just giving. Then now it comes to breakthrough innovations in HFSS. What happened over the years on the development side? So they started this adaptive meshing in 1990s. So it is almost like a 30 years old technology, but improved over the years by adding a lot of high performance uh, high performance techniques into it by improving the solver calculations and other things. So this first thing is adaptive meshing. Then they use the multi-processing on the core, then integration of in method of moment solver. Then they added these arrays techniques, GPU for calculation for FEM and SBR, then broadband meshing. The final one, which is coming in 2021, was mesh fusion. Mesh fusion is a new technology introduced in this year. So we will check what is that mesh fusion. Then we will go into review of HPCs. Okay. So mesh fusion, what it mean by mesh fusion is, so just see this particular video. So this is how the RF, the IC module will look like. So if you zoom into each and each sections, right, you will see a lot of components in it. So this is a IC module. Then you can see the wire bonds. And this is the IC. You can see this is IC. Then you have a PCB over here. And this, if you go and see, there are some antennas over here. This is a mobile which has processor plus memory, which sits inside a vehicle. So you can see an electric vehicle model here. And this is the final model. So this is a anechoic chamber where you can see a horn antenna which is radiating high intensity field towards your vehicle, and you are doing radiation susceptibility electromagnetics analysis. So what it shows you is you have a big problem, which is a big anechoic chamber with an horn antenna. Then there is a vehicle. Inside a vehicle, there is a mobile. Inside mobile, there is a PCB. Inside PCB, there is an IC, and there is a die over here, RF die. So you are actually solving a problem which is in the order of meter. When it comes to die inside this die, it will be on the order of micrometer to nanometer in size. So you're solving this structure which is in nanometer to meters in size. Meshing is totally difficult here. You can't preserve a mesh with a micrometer size to all the way to millimeter meter size, and that going to kill your measure. So meshing is a one big challenge for electromagnetic problems to get accurate result. If measure is not able to mesh your structure, then you can't even solve it. You need a mesh to solve it, right? So this is a mesh fusion. What it does is whatever the geometry you have it independently mesh it. What I mean is your die will mesh independently, your the IC plus PCB will mesh independently, your vehicle will mesh independently, your anechoic chamber and rest of the geometry will mesh independently, and then solve this or integrate this mesh together using a fusion algorithm. Okay, that's what this mesh fusion will do. So one example will be, I have a simple transmission line. There is an inductor here. Okay. And what it does is when you do the mesh fusion, for simple analysis, if I plot the mesh across this geometry, the mesh around this air and PCBs are totally different compared to the mesh which is inside the component. What it means is this block is independently meshed and the other extra boundary is meshed independently. So what is happening here is the meshes are discontinuous at that point. If the meshes are discontinuous electromagnetically, it is difficult to solve it. This mesh fusion not only mesh the component independently, when there is a discontinuity in the mesh, it properly take the electric field propagations here. So even though meshes are discontinuous, you can clearly see fields are continuous in the boundary, and there's a simulation domain. So it's not only mesh fusion is not only just a independent machine. It on the electromagnetics calculation also there are a lot of additional challenges they were faced. They improved that one. They corrected it. Now this is available for you to solve it. So now, as per Ansys point of view, now there is not much challenges. Any problem, all the way from nanometer to meter or nanometer to kilometer, you can solve right now. So what it means is these are different types of meshing technology. So in a simple simulation, different meshes are working parallelly and then solving it. So this is a simple max filter problem. What I did is I divide this into two problems. So this will mesh separately, this section will mesh separately. And you can see the fields plot. When I plot the field, you can see these fields are pretty much identical. S parameters are same. You can also see the memory and simulation time. Memory reduced by 1.6 to 1.2, 8 minutes simulation reduced to 5 minutes, 36 seconds. So you will see the improvement. And when it comes to another one, this is called the Electromagnetic Emi Emc problem. You will have a antenna which will receive the emission from the your mobile laptops. It can also radiate and impinge some unwanted signal into mobile. So there are analysis called electromagnetic emission and susceptibility problem. So this is an example of that. So this is having a laptop with the PCBs and couple of antennas. It was not able to simulate it in earlier version because you have very small component and very big geometry here. But with the mesh fusion, you can see the meshing completed just under 4 minutes, and simulation time, it still took 80 hours, more than 2 to 3 days. But it solved this problem using mesh fusion. Okay, so there is no limitation. So now people can simulate huge problems with HFSS. So this is a touch panel display. So 300 micrometer level touch panel features are there inside it. It is able to solve that one, including the anechoic chamber scenario. And these all are different problem, which was earlier was not possible to simulate it. Now it is possible to simulate with HFSS. This is what mesh fusion talks about. This is on a PCB. You can see the with and without mesh fusion, right? You will see significant changes in the meshing time. 2 hour with the normal meshing, mesh fusion just 53 minutes. And when it comes to total simulation time, because of the mesh fusion, 77 hours reduces to 2 hours 59, max close to 21 hours. So significant speed up in the simulation time. The S parameter for normal meshing and mesh fusions are exactly same. So it proven technology now you can use mesh fusion for different applications. So it improves this, it significantly it reduces the meshing time. It reduces the memory consumption for different process in the computer, in the computation. Okay, now this is just we talked about some of the application of electromagnetics, what is new, which came in 2021 in electromagnetic computation point of view. Then the second question is why we need a high performance computation. So the question is, when it comes to 1990s, the HFSS started most of their code in that time, 1990. In that time, the 10K matrix size. So this is nothing but a waveguide with a coaxial adapter, and that is only half portion of it. It is the number of total number of matrix size is 10K matrix size, and it took 10 hours plus on that time on a machine to simulate it. And what has happened is simulation requirements now scaled up to, let's say, big vehicle with the antennas and big anechoic chambers. It became very complex nowadays. You can see the PCBs with the connectors and another memory module over here. So you can assume one motherboard PCB when it comes to a computer motherboard. Those are like 24 layer to 36 layers PCB. So the PCB with the connector and a memory module, those kind of complexity now people are trying to solve it. And another one is hardware evolvement, right? Earlier machines were very bulky and is very slow in computation. Now, if you come to the hardwares, right, the 10th generation, 11th generations processors and other thing, the huge speed up came both in hardware side. This is very obvious. People are aware how the earlier in my side, my studies time, these floppy disks and other things are very common. That 1.4 MB of memory was sufficient for copying files here and there. Now we have SSD cards with the 256 GBs and other thing. That's the kind of hardware changes happened over the year. Coming into current challenges, right? There's some couple of challenges are, as I mentioned, the PCB with the connectors and the memory modules. Another example is 5G. 5G requires huge MIMO antenna arrays. So that is another kind of requirement. And you might have seen the automotive vehicle, automotive radars, right? So you can see the vehicles are moving over the road and how it is going to detect the targets and other things. So automotive radar is another kind of big EM challenges in front of us. Coming into on chip, so if you see the scale up, how the electromagnetics simulations evolved over the year. So you can see in HFSS version 1 in 1990, as I mentioned, 10K unknowns. were taking almost like 10 hours. When it comes to 10 years later, we came to a situation to solve up to 0.7 millions of unknowns. In 2015 to all the way to 2020, different technologies are developed with a different thing. In 2019, the maximum unknowns we solved was 9.5 millions, which is 2 by 2 IC. So this is a IC, you can see. So IC, when you zoom in, right, you will see very complex structures here. So rather than big problems like vehicles or aircraft, computationally, these kind of problem when you comes to the processor kind of area where the RF domains are located, the Qualcomm chip, 5G chips and other thing. Where if you zoom in, you will see these kind of RF components here. So in 2021 and 2020, this is actually 2020, they went up to 102 millions of unknowns, which is 30 meter, 3 centimeter by 3 centimeter RFIC. They solved with 102 million. So you can see 10K unknowns to 102 million unknowns currently this capability. Now this is again further improved in 2021. We will be updating this particular slide. The scalability, you can assume something like this. This here, the scalability increase something like exponentially, and that will increase over the year also. The solvers are not only because of the hardware, this software side also we need a lot of improvement to solve this problem. So what are things you can implement in order to improve these simulations? So one is if you take a processor nowadays in your machine, you will have multiple core in it. So HFSS simulations will speed up across multiple core. So multi-processing was the first technology, then they developed with the multiple processing technology. Now this thing come with a multiple core. So nowadays, if you buy a system, it will have my laptop, which I am presenting. It has 8 cores in it. So you can distribute simulation in a single CPU. You can distribute simulation into 8 cores, which solve the problems much faster, and you can expect almost like a 4 to 5 times speed up. So this is a I guess a 10 millions metric size. This particular PCB, you can see this speed up over here. If you change from 1 core to 10 core, you are almost going to achieve by 5x kind of speed up. Okay, so the speed up is it is not purely linear. At some point, you will see some it's going to straighten up, but the speed up is increased over the mic or over the course. Okay, so one way is use multiple core in your CPUs. Another one is you can increase the simulation time using GPU. So FEM solvers now supports GPU. One solver called direct metric solver, which solves GPU. You can see the scale up is up to 2x times. Some cases you can see over more than 2.7x times using the GPU computations. So what they integrated is along with this metric simulation solution or calculation, they added a couple of simulations with the GPU. So some of the complex metric calculation now GPU can perform it and speed up the simulation. Another one is most of the time when you see these complex simulations, right, one machine may not be sufficient in order to simulate this kind of problem. So what you can do is you can distribute the memory across multiple machines. So I have a one machine with a 64 GB. Then I use a multiples of 64 GB and connect between machines using a good high speed network cable. It can be a 100 Gbps more than that LAN cable, or it can be an infinity band kind of cables where Gbps connection can be possible. So that because huge amount of data are going to share between different machines. So you need high speed connectivity between the machines so that speed will be more. Okay, so that's another way. So you can see an example, a vehicle, complete vehicle body with an antenna, a human body model, and this was solved with a 6 machine of 128 GB under 3 hours. So this took totally 714 GB of memory, and it able to solve the complete problem. So this done in 2014. So in 2014 itself, they implemented this technology to distribute the simulation across multiple machine and solve it. And when it comes to complexities, right, you may see the complexity going to be huge for big problems. No, this complexity going to be big challenges for this kind of problem like PCB, die, processor, RFICs, and other thing. There you can see this complete PCB was simulated. It's a 8-layer PCB. 64 signal lines means 64 high-speed signal lines from memory to all the way to processor. They used 128 core. Total simulation time is 7 hours, 21 millions of unknowns. And it took 72.75 GB of RAM. Not 72.75, it's actually used, I think, around 4 or 5 machines. And each machine it took 32.75 GB. So in the next one, you can see the total memory was using by 262 GB. And there were 8 machines. So that means one machine was using 32.75 GB. So this was a complete S parameter between the memory module to the connector side of this SS, the memory module, the DDM memories. Okay, so that's one way is, as I mentioned, you can speed up the simulation using multiple core in your CPU. Another one is if you have multiple machine, you can distribute across multiple machine. If you have a GPU in your machine, you can distribute the simulation, or in further speed up can be possible by using that GPU also in the computation. Another one, so the simulation actually takes in the process of meshing, then solving and finding the right mesh for your structure by using adaptive meshing. Then you need to solve for a frequency band. So another kind of a HPC is called spectral decomposition method. What it you will do is, let's say I want to simulate this PCB with a connector or package, IC package from 0 Hz to all the way to 20 gigahertz. I can distribute multiple frequency to multiple machines. So over here, this technology was started in 2013. So 2013, a simulation was taking about 25 hours, and just by uh, 1 year, the improvement when it starts solving frequencies parallelly. Instead of solving one frequency, I can solve 5 or 6 frequency parallelly. And there you can see the huge speed up just by a solver update itself. It 25 hours reduces to 14 hours. And when it comes to frequency sweep with the multiple machines. So here it used 32. When it comes to 128, the simulation earlier was taking 8 hours. In the next release, it was taking 3 hours. So 25 hours of simulation can be significantly reduces to 3 hours by using multiple machine for solving frequency points. So one frequency will be solving using one machine, another frequency will be in different machines. Like that, you can use multiple machine to speed up again. So these are some of the example. Another one is you may be interested to see the field, but 90% of this PCB analysis and other thing, right? People would like to see the S parameter. So if you are okay with S parameter, then there is a significant speed up they added on the S parameter extractions. So if you want to solve the field also, the memory requirement was 97.3 GB. But when it comes to only S parameter, that memory reduced by 31.2 GB, and that reduces the memory requirement by 3.1 x times. And simulation time also improve a lot. I'll show you that example here. So you can see the same example model with the field and without field. So the field is nothing but the electromagnetic field. If you want to visualize, that is a simulation on the left side. If you are not looking for the field, but I am looking for the S parameter only, then you can see the simulation time without, uh, okay. This is what with the field. There is a correction here. This is with the field. It was taking 8 hour 33 minutes. Without field, you can see just simulated under 4 hours. So, almost like a half times reduction, and speed up is about 2x times. So that is another kind of options of using HPC. So HPCs are leveraged across a different way, core, mem, different core, different machine, different frequency solving parallelly. Another method is decomposition method. I'll explain you on the decomposition side. Let's say I have a big problem, big aircraft, I want to simulate it. What I can do is, instead of solving this problem in a single machine, I will distribute into different machines. What it does is different structure or different areas of the regions will be distributed to different machines. Then one machine will control the entire process. So that's called a domain decomposition method. So the entire problem will be divided into different machines. Earlier, only memory was dividing, but here the process itself is going to divide. And you can see the comparison between normal simulation and domain decomposition simulation. Results are validated against so many different models. And we found this method is also another way of improving the simulation time. Another one is hybridization. What I mean is, right? Hybridization, I told you, you can ask HFSS to solve different solver for different geometry. One is, the FEM actually, the unknown which FEM solve calculate is the electric field, but the integral equation, the surface current is a solution. So you don't need any radiation boundary for that. So if you integrate FEM and IE hybridization, so over here you can see 137 GB of memory and 2 hours, 16 hours of simulation time. Now that's reduces to just under 5 GB of memory and 6 minutes. 23x speed up in the computation, 27x speed up reduction in the memory. So this is nothing but what it does is FEM actually calculating the electric field, and then on the surface of this radiation boundary, it will calculate what is the surface current because of the electric field. And then once it calculate the surface current over here, then entire problem become method of moment. And large metallic area, method of moments works pretty nicely. So that's the idea of the entire structure, entire method. And this method, the domain decomposition, now available under antenna array also. So the antenna arrays problem also, we now using the domain decomposition method for large antenna array elements, and this is also can be used HPC technology, which I mentioned in across different core, different machines, then solve it. So the one of the example is a big 256 element 5G MIMO antenna array at 28 gigahertz, and this consists of 4 subarrays. This is 64 element subarray. This is another 64 element subarrays, and this salt in a 128 core machine means around the 5 machines of 32 core just under 2 hours. So you can see this complete simulation, including the radome, antenna array, and the ground plane. Next one, so far we discussed about PCB, IC, antenna, then little bit of automotive. But now let's talk about radar simulations. HFSS is capable to simulate automotive radars or defense radar, which can work in FMCW method or pulse radar method. So when it comes to a simple radar, right, it actually starts, let's take an automotive example. So nowadays you might have seen Mahindra launched a, level 2 autonomous machine, which has a camera over here and there is a radar over here. So it will look something similar to this. When it's zoom in, you can see some area like this. In Mahindra, it is somewhere here. They were using Manto radar for automotive. So over here, what you can see is there will be a radar. If you go a little bit behind, it will look something similar to this. This is called the dielectric lens or dielectric material. Behind this, there will be bracket, radome bracket, and antenna. And how it is going to work is, so let's say this can be simulated fully in FEM simulation or with SPR simulation. Okay, in SPR, you will simulate the antenna in FEM and the rest of the geometry will be simulated using SPR region. This can be simulated. So you can see the simulation time. If you are using full FEM, it was taking 4 hours 14 minutes and 101 GB of memory to solve it. But the same model I simulated with the SPR. I mentioned SPRs are for electrically large problem, but when it's simulated just under 2 hours 50 minutes. 4 hours 41 minutes reduces to 2 hours 50 minutes. But there can be small amount of uh, accuracy issue because SPR are using the optical method, but it more or less looks very identical between these two solvers, two results. Okay, so the another method is using SPR with the graphics card, the GPU with the RTX 5000, huge simulation speed up here. And when it comes to radar simulation, right, I'll show you this example. This is actually, I took the video from YouTube. The people have actually simulated, measured the radar response. You can see the radar, the target is also detected. Here you can see the reflections or rotation of Doppler because of the tires. So these tires are in front and back tires. So you'll clearly see the reflection which is coming from the tire here. This is called micro Doppler effect. We also simulated same scenario in HFSS. Here also you can see the front tire and back tire micro Doppler effect. So HFSS radar simulations are well validated against measurement. I have so many other validations and they use this kind of a technology, shooting and bouncing ray technology, in order to solve these automotive radar problems. This is now we are using for a little bit of defense application also. Uh, Over here you can see example where let's assume I have a radar antenna. There are two vehicles. If you see these simulations, how it is solving, that's what I am trying to explain here. If you have an antenna, it actually shoot a lot of rays and depends on the material property of the medium. Rays will reflect it. And if it is reflecting on the road, some part of the signals can still propagate even though there is no line of sight between these two vehicles. If you see from this point, because of multipath, it can propagate to the uh, non-line of sight area also. Okay, so total number of reflections will be are there. After the reflections, there can be some rays which can penetrate through the dielectric material. So if from here, the ray can directly go and hit on the glass body. There can be some rays hit on this road and then go and hit on the glass body. It can propagate through these inside medium and hit on the vehicle which is in front of it. So the total simulation for this one, actually it's going to send about 1 to 10 millions of rays per pulse of radars. So you need to have hundreds of radar pulse in order to get a single frame of range Doppler velocity. So it's a combination of both transmitted and reflected rays. And this is what happening when you actually move your vehicles in front of the radar, right? So many number. This is actually filtered because if you allow to render all 10 millions or 1 millions of rays, the graphics will hang. So we reduce the number of rays in the visualization process just to show you how the electromagnetic pulse is going to interact with the ray tracing method. So this is what happening in the background. Then if you want to see the time domain analysis, we can convert this near field data from the frequency domain into time domain, and you can visualize how the electromagnetic wave is going to propagate from the vehicle, how it is going to uh, reflect based on the geometry which is in front of the radar. And this radar signal is actually coming back to the signal. So this is called, you can say this is what happening in radar, which will detect the range and velocity. So when the electromagnetic wave is propagating, the wave which is propagated depends on the material property. Some energy will be reflecting back. That's what it calculates. Okay. So when it comes to a large scenario, this is a big city scenario. In 2019, what happened is if you want to simulate this scenario, it was taking about 14 hours of simulation time. So that was a computation required for HFSS in 2019. Then what they did is they created an algorithm. It's called accelerated Doppler processing algorithm, which reduces this computation time to less than 5 minutes. Then what they did is they created one more algorithm. It's called fast frequency looping method. They improved the simulation again to less than 1 minute. So by 2020, what they did is uh, 14 hours they reduces to 1 hour just by algorithm developments, the soft solver improvement, you can say. So almost like a 1000x speed up by just algorithm. But what happening is in the if you want to run a real-time vehicle, then you need to create each frames at least 30 frames per seconds. Okay, you can see that every 30 milliseconds, close to that, you need to have a one frame. That's kind of speed up is required, but it's still not able to create a 30 frames per minute. It's still less than 1 minute. So what they did is they implemented this complete accelerated Doppler and frequency looping method in GPU computation. Now they are able to create one frame under just 20 to 30 milliseconds of time. The hardware acceleration is about 3x times because of the GPU. And total acceleration, which just developed in 2 years, was just 3 million times. Because of that, you can see this is a radar with a vehicle with a multiple radar. Now what you see in the Mahindra's XUV is just one radar. But if you want to go to L3, L4, L5 kind of autonomy, then you need multiple radars around it. And that has to simulate kind of this kind of environment, virtual environment, because testing in actual road going to take a lot of monies and time. A lot of noises also can come in. But what you can do is you can run this kind of simulations in real time in a simulation environment and see how the radar going to detect each target if the radars are placed at a different location of the vehicle, and then you can do the signal processing method and detect it. Over here it simulated for 1 kilometer distance, 17 vehicles, 14 buildings, 375 lightning posts and other thing, and this simulated for 20 seconds, 600 times 3000 images, and used this RTX A6000, not 60,000, 6000 GPU card, which is capable to generate 17.6 milliseconds for one frame. That means 50-second frame per seconds for 5 radars. That is the capability now it generated because of this. So this is another example where you will see the micro Doppler effect. This a micro Doppler is another effect of radars which can detect the rotation of radar, the tires and other thing. So you can see the micro Doppler effect which is detecting by the automotive vehicles. This is another object detection from the real-time radar. So you will be able to see how the vehicle is propagating and where all the target is reflecting back, how the range and velocity plot will look like when this vehicle is propagating around it. So this kind of speed up they developed using this particular algorithm. So as a conclusion, so multiple antennas will be there in a single radar. It extracts this frequency pulse information for different channel. It can be used for detecting the range of a target. It can be detecting the angle of arrival of a target. It can be used for ISAR imaging, imaging of the terrains and other thing, and different other applications. Finally, you will see something like this. You can see which angle these targets are reflecting and what is the distance is the radar is going to come. This kind of plot with the full sphere, which is common for search and track radars, and for automotive application, you will have a field of view. Okay, so the current capability is uh, 15 channel radar. You can simulate with the 30 frame per seconds with the real-time capability. When it comes to 110 channel radars, right now the speed is 4.4 frame per second, means close to 4 to 5 frames you can generate over the time if you have a 110 channel radars. So that's all the capability of the current HPC in the electromagnetics. I think I could able to convey some of the scalability, how the electromagnetics solvers are scaled up over the years in the industry. Is there any open questions?
Thank you, Nijas, for a wonderful presentation. Let me check if we have questions in the chat first. Yeah, there are a couple of questions. One is, can I get the PDF that you're teaching? So,
Yes, I'll share it with Abhimanyu. You can share it
okay.
there.
So I'll share the sanitized version with the organizers, and they can share it with the participants. And second question is from Dr. Prashanta. What is the computational time for building a busy road simulation with radar?
Okay. So this, as I mentioned in the last slide, this was real time. Uh, every 30 millisecond you can generate the result of the entire buildings and other thing. So if I go a step back, right, this contain road with multiple vehicle, and if I go back here, this is with the multiple radars on a vehicle with so many street lights, multiple vehicles, buildings and other thing. It can still create 17 milliseconds. Every 17 millisecond it create frames. Okay, so that kind of a speed up. And this is not right now integrated with HFSS. Why? Because HFSS graphics in user interface, right? It's not designed for uh, taking this kind of complex rendering. So this is in the same solver integrated. It can be integrated to any platform. It integrated with the Carla automotive radar simulator. It integrated with the Ansys VRX virtual reality graphics engine. So that I think today second half you will have a talk on that. So this solver is integrated, same HFSS solver is integrated inside this particular uh, tool to get a feel of movement of the graphics movement, but the computation is same as in HFSS. Now what you have in HFSS is this 14-hour simulation. Now you can simulate just less than 1 minute. That capability current HFSS has. If you have this scenario, I have so many models which is now available in the next year. It is in the open example. You will have this kind of a lot of example which can simulate, create this kind of a frame in a very less than 1 minute time.
Okay, thank you. So similar question, can I get PDF of previous day that you had taught? So yes, we had one session from ANSYS yesterday by Dr. Wimslater. So we'll be sharing that presentation as well. Regarding other sessions, I'll discuss with Professor Pavitra and other coordinators, and we'll share those presentations as well in PDF format. So those are all the questions that I could see in the chat. And if there are any more questions, audience, please feel free to unmute yourself and ask directly. So Nijas, it's okay. We can wait for a couple of more minutes.
Yes, yes.
Okay, thank you. Yes, so Professor Somnath sir has already written that the first day's PDF will also be shared. So post completion of this HPC workshop, we'll share recording as well as the PDF copies of the presentations with all the participants.
Okay, there is
We have
one
one. Yes.
question, right? What is the possibility of solving particle-based method using ANSYS? The electromagnetic side, we are not currently not possible to simulate particle-based simulations, but from the Fluent team, they can comment on the fluid dynamics side, but electromagnetic particle movement like a Klystone kind of simulation is not possible. But you can do something like a multi-paction RF discharge simulations with HFSS, which predict what power your device going to break, or arc is going to come, or breakdown going to happen. That you can predict it. But particle based one, the other physics people also can comment over here.
Yes, so on the particle side, Nijas, we have Rocky DM, wherein we can solve the shape of the particle interaction, and it has a very seamless coupling with both mechanical as well as CFD side.
Yeah, and to addition to that, Abhimanyu, we have the SPH module also of LS Dyna, which is particle based model.
Right. We'll start next session immediately after this one. So please stay tuned in. Just we are waiting for if there are any more follow up questions. We'll take that up. So I don't see any more questions, Nijas. So in the interest of time, we'll wrap up. But if there are any follow up questions, audience can always write to us, and we'll be happy to connect.